So midway through the Torricelli's law lab, we end up with an equation that relates height, y1, to how fast the water comes out of the hole. And it's important to collect data that investigates this pattern. You can solve lab data for one trial, which I actually do here, but it's not as helpful as collecting data for lots of different heights of the water and lots of different velocities, because then we get to check if this pattern holds true across a wide range of values. It's sort of a validation of whether the theory base we used, which is really Bernoulli's equation, is appropriate for this situation. The way to do this is something called linearization. And linearization in physics always pretty much works the same way. You start with a fundamental equation, in this case conservation of energy, Bernoulli's equation. But it also could be sigma F equals ma. It also could be some other important equation that you derive. You work it down until you've got an independent and a dependent variable on opposite sides of the equation. And then you try to fit it to the equation of a line, y equals mx plus b. This process is called linearization, and I'd like to, in this video, show you how to do it. We're going to start with linearizing Newton's second law, A equals F over m, because that's a familiar law for everybody. So on this graph, what we're seeing is that acceleration is equal to some number divided by mass. And that another way of saying that is that acceleration is proportional to mass. So that's one of the big ideas of this lab. And what it can be translated into is that as mass gets bigger, acceleration gets smaller. Because if you have a bigger number on the bottom of a fraction, that makes the overall fraction smaller. So we're going to try to analyze that hyperbola, or that rational graph, to try to figure out if we can get some important information out of it. The problem with a hyperbola is that most spreadsheet programs can't fit to it, and that's actually true of a lot of the functions we're going to want to study, especially in the college level physics classes. So we have to have a technique to transform the data into something we can work with. And we're going to use a technique called linearization. So I want to walk you through it for this particular lab, and we will hit it again and again and again as we go forward. Just one thing to understand, y equals mx plus b, our slope-intercept form for a line. From here on out, I'm going to write it y equals kx plus b, k for constant. And it's just that we're using m for mass. So this doesn't look as familiar, but I think it'll stop us from being confused. Here's some data from one of my periods in 2016-2017. As we saw from the previous data, which is really typical for a class, it's not easy to tell that it's a hyperbola. And that has to do with how hard it is to collect this data. But this particular class during that school year did a very, very careful job. And we'll have some evidence for how careful they were later. But it's not hard to imagine that that could be a hyperbola. So we're going to use this data because it's going to help us make more sense of things. We expect this to be of the form A is proportional to 1 over m. As mass gets bigger, acceleration drops. And that means we have the equation A equals k over m. There's a proportionality constant. There's some number k here, but the big idea is that as m gets bigger, A is going to get smaller. I'm just factoring out the k, so I'm writing A equals k times 1 over m. Now why would I do that? What's useful about that? If I factor that k out, A equals k over m becomes A equals k times 1 over m. And that makes it really easy to line up against the slope-intercept form of the line equation. X kind of takes the role of 1 over m. Y takes the role of A. And then we're left with the slope just being the slope. The fact that these line up so nicely together tells us something amazing. If we treat 1 over m as our x-axis and A as our y-axis, we should get a line, even though our original graph with mass on the x-axis gave us a curve. So this is transforming our data to make something that the spreadsheet program and us can't fit into a new equation, a line, that we can fit very easily. So what is 1 over m? It's literally just 1 divided by the mass. So I'm telling the spreadsheet to copy the masses down, but instead of writing them exactly, do equals 1 divided by the original mass. That's going to get me the inverse mass. Acceleration, I literally just copied down. And if this is really a hyperbola, then if we graph a versus 1 over m, it should be a line, according to the fact these line up together. So we do that, and we get something that looks really linear. So here's another linearization, which I think you probably saw in a previous class. Here we're starting with Newton's second law, sigma f equals ma, and our free body diagram, and we get down to this equation here. K delta x is mg. And we could treat mass as an independent variable and delta x, how much it stretches, as a dependent variable. So if we rearrange this equation so that it fits next to y equals mx plus b, this tells us that a graph of mass on the x-axis versus delta x on the y-axis, that should help us get a linear graph, and the slope of that graph depends on both the gravitational constant and the spring constant. So if we were trying to find either of them, we could get the slope of that line, set the slope equal to this, and solve. Here's another one. You may not have seen this depending on which class you took before this one, but this is the equation that relates period of a pendulum to length of the pendulum. And you could get a linear graph in two different ways. You could take this one, factor out square root of L. In other words, change the length of the pendulum to lots of different lengths, and we expect that to affect the period. The slope of such a line depends on the gravitational constant and pi, basically. The other thing we could do is we could square the whole thing and graph t squared versus the length of the pendulum. Depends on the same things, the slope will have a slightly different meaning, but those two are equivalent. The key thing is in all of these cases, we line up the equation we're trying to linearize with y equals mx plus b. And then we circle up. The thing that gets circled with y, that's what we put on the y-axis. The thing that gets circled with x, that's what we put on the x-axis. And whatever's left over is going to be the slope. You set the slope equal to whatever's circled with m, and you can solve for something. So, in the Tortelli Law Lab in AP Physics 2, I think this is the linearization you might want to do. And that's what I'm going to have you guys do in the lab packet. And if you think about it, the slope in this case could get us a value for g. Let's graph our data and get ourselves a value for g.